Great pleasure to be here in this beautiful country, more beautiful than Hawaii. I am blown away by Brazil. It's my first time. I also am enjoying your language. I speak Spanish, so I'm starting to understand a little Portuguese. It's lovely. I'm on sabbatical right now at the University of Heidelberg at the Center for Quantum Dynamics, and then I'm based at the Colorado School of Mines in Golden, Colorado. This is work that I've done in collaboration with an outstanding PhD student, Michael Wall, and I'm supported by the von Humboldt Foundation and a number of other agencies. Okay, so I'm going to start with general considerations and motivation, and then I'll tell you about the molecular Hubbard Hamiltonian. I'll talk about the natural many-body regimes of different molecules. One of the main themes of this talk is that different molecules exhibit different many-body physics that's quite different from atoms, right? So for atoms, we have these Hubbard models. All the Hubbard models basically look the same. It's independent of whether you're using, rubidium or potassium or lithium or any other atom you like. For molecules, that's not the case at all. Molecules are complex objects with many internal degrees of freedom that gives rise to new many-body physics. So that's the main message of this talk. I will now back that up with an hour of conversation, but that's the main point, okay? At the end, depending on time, I will talk about applications in terms of phase diagrams, a new concept in molecules I call tunable complexity, and quantum dephasing. This in particular is easily observable in experiments. Okay, I'm going to start with a picture of my group and with Michael, who I work with. I'm very proud of this PhD student. I have a wonderful group at School of Mines. Apparently my group is quite small compared to what you're used to in Brazil. So in the US this is a big group, but here this is just a little drop in the ocean. And I have an open postdoc position I should mention for fall 2012, and year-round I accept applications for master's and PhD positions. Not all of you may be familiar with the state of Colorado. I understand there are, is it 26 states in Brazil? Am I right? Or more lately? No, only 26. You haven't conquered any neighboring nations recently? Okay, so, and I've seen only 2. So you may not be aware of Colorado, so I'll just show you a few pictures. Colorado's a little colder than you're used to. We have wonderful skiing. You really do see cowboys out and about in Colorado. I guess Argentina also looks something like this. Yeah, we have our own large animals wandering around the mountains. This is a mountain lion. I guess he's small compared to the jaguar, but compared to some other cats you have, he's about the same size, about this big without the tail. And we have incredible national parks. This is a very famous one. It's a very interesting, complex system. People analyze it through nonlinear dynamical methods, actually. So there's physics to understand this system. This is called Great Sand Dunes National Park. There's a glacier up here. There are salt flats out here with buffalo wandering around. There's a river here and a forest here and 2 mountain ranges. And all of these conspire to give rise to 30-meter high sand dunes, some of the highest in the world, at 3,000 meters. I have to convert into meters in my head, sorry. So, this is a really beautiful place to go. And it has its own adapted wildlife that lives only in that location in the whole world. Okay, I'll tell you a bit about School of Mines. We are a public polytechnic university. The university is actually the first in Colorado, and it was founded to increase safety for mining operations. That's how Colorado began. I understand you also have a major area that began with gold mining and whatnot here, so this is a similar story in Colorado. Of course, today it's a general polytechnic university. Our special focus is Earth, energy, and the environment. We have the National Renewable Energy Laboratory in our city. We have a joint institute with them. Although I don't do this kind of research, I personally think it's very exciting. The university has save the world mentality in terms of development of alternative energy resources. Like photovoltaics, biomass, et cetera, and that's a big focus of the university. So they're actually the national center in the US for doing that. We have lots of different degree programs, about 5,000 students. You can see our grant level, about 1,000 graduate students. So we're quite small compared to you, but I think what we do is good. Our physics department is about a mid-sized department for the US, about 30 faculty, 10 teaching, 20 research, 250 undergrads. Okay, I think you have 600, is that right? Something like that? Yeah, we're one of the 5 biggest in the U.S. The only comparable programs are at MIT, Berkeley, University of Washington, and one other. So, for us, this is big, okay? And about 80 graduate students. We're very heavily focused on condensed matter. We have 4 major research centers, one, of course, in renewable energy, and we have a very nice joint program with applied math that I co-chair. So I think it's a nice small university to be at. We're right near JILA, which is a major area of development, a major institute in AMO physics and ultracold physics. And in general, in the Front Range, we have an incredible scientific community. We call this Front Range this area where the mountains meets the plains in the U.S. So within, I guess for you, it would just be the city of Sao Paulo. For us, it's like 5 different cities. Within about an hour of driving, we have 9 major physics institutes, either universities, national labs. We have NIST, we have National Renewable Energy Laboratory, we have National Center for Atmospheric Research, we have Aspen, Telluride, and then major R1 research institutions, including ours. So it's a very exciting place to be. I think in the U.S. it's second only after Boston, actually, for research area. So that's Colorado School of Mines. Let me tell you a little bit about what I do. So I work in quantum many-body theory, in artificial materials, and in nonlinear dynamics. Today's topic crosses between far from equilibrium quantum dynamics, I'll get to that just at the very end of this talk, and ultracold quantum gases and optical lattices. You can think of this as an artificial material. So if you use these systems as a quantum simulator to treat otherwise unsolvable Hamiltonians from solid state, then I would call this an artificial material. I think ultracold molecules is the next wave of ultracold physics. Incredibly exciting. About half of the research in my group is now dedicated just to this topic. Okay. So the application date for this workshop is already over, but I just want to show it to you because this, this is something I'm organizing, and it shows you what's going on in cold molecules. Okay? So this is going on in KITP in spring 2013. The date just passed, but let me show you the topics. So what's going on in ultracold molecules? I'm just going to talk about one piece. It's a very big area. Chemical interactions of molecules at sub-Kelvin temperatures. So that's already a whole new area of chemistry where you have chemical reactions that scatter into just a few partial waves. Okay? Few body physics, like Efimov states, 3-body recombination of ultracold polar molecules. All unsolved, all unknown, all new. Fundamental symmetry tests with cold molecules. You can look for time dependence of alpha, for example. Okay, there are wonderful things you can do with cold molecules. Quantum information schemes look very good. This is not just talk. This is serious. Okay. Many body physics and quantum simulation with new internal degrees of freedom. That's what I'll talk about today. Advances in molecular cooling techniques. I mean, I guess as a theorist, these are theory-oriented topics, and this is a theory workshop, Kavli Institute for Theoretical Physics. But this in itself could be a whole workshop, right? I mean, that's incredible experimental developments since 2008, 2009, and there are many new applications of ultracold molecules. So I have a review article in this area, which people may find useful if you're interested in ultracold molecules. It's in New Journal of Physics. It's from 2009, but people are still finding it quite useful. It's not yet out of date, so you may wish to read that. Okay, let's go on to my particular interest in ultracold molecules, the molecular Hubbard Hamiltonian that we've developed within my group. So what is it about ultracold atoms in lattices that's so exciting? So for me, what I find very exciting is that I can explore a topic that I think is very beautiful and foundational. That is the topic of quantum phase transitions. And in particular, what you can do here that you can't do in solid state is look at the dynamics of quantum phase transitions. So the many-body dynamics is very slow. It happens on the time scale of milliseconds. In solid state, picoseconds, something very, very fast. And, you can get a lot of information out of the system, because you can access the sites individually now in experiments. So, for example, this is a well-known experiment from 2002 in which, so does everyone understand that there are lasers interfering to make this optical lattice? Is this group familiar with this kind of technology? And these red things are atoms wandering around the lattice. Okay? This is one phase called a superfluid phase where the atoms all talk to each other. They have a coherent phase. You can think of it as an extreme of the number-phase uncertainty relationship. The number is unknown, but the phase is very well known. This is another phase. The lattice is made higher, and it freezes out into something like a crystal. It's called a Mott insulator. Okay? Then the number is well defined, but the relative phase between sites is unknown. So if you go through this phase transition, what's been seen in experiments is it goes through actual oscillations. You don't just jump into one phase and you're done. You actually oscillate back to the original phase, back and forth, and damp out. Okay? That's not something that we would have ever seen in solid state. Okay. What's exciting about molecules? What's new about molecules? Okay, molecules are already at the edge of quantum degeneracy. I mentioned the work from JILA simply because I live 20 minutes from JILA and I talk to them all the time. There are lots of other great experiments. No bias implied. This is just my local experiment, so to speak. So they have rubidium-87, potassium-40 in the absolute ground state. The way they do that is they start out with very cold rubidium-87 and potassium-40. They sweep it through a Feshbach resonance to get these atoms to join to make a very floppy large molecule on the size of 10 to 20,000 Bohr. And then through a technique called stirrap, they connect via an intermediate higher state all the way down to a ground state molecule of just a few Bohr. So this is a very remarkable process, right? You have to get overlap between something that's 10,000 Bohr to something that's like, 3 Bohr, right? So that's what this intermediate state does for you. And I guess one of the key, I'm not an experimentalist, but one of the key steps in the experiment, in that particular experiment, was use of a frequency comb in order to have a well-defined phase reference between these two frequencies of lasers. Okay. So molecules offer new handles compared to atoms. They have a dipole moment. That's a long-range interaction. Everything here is contact. The atoms don't see each other unless they're on top of each other, right? Here we have a long-range interaction, falls away like 1 over r cubed. They're not electrons, it's not 1 over r, but it's something like magnetism, right? Molecules have rotational states, right, because they're dimers. And the dimers are heteronuclear. One side is big, one side is small. Do I have chalk, by the way, in case I want to draw anything? I don't see any here. Behind me. Ah, thank you. Great. So, right, so these, stick and ball model of molecules. These molecules look like this, right? Okay. And there's also nuclear hyperfine structure. So within each atom, there's some kind of spin that can be controlled by magnetic fields. So I'm going to talk about how to control these different degrees of freedom, that one and the one that has to do with rotation, okay, and how to control them separately. I'll present that in great detail. Okay. So let's address some questions. So first of all, what is the most experimentally natural, easiest lattice Hamiltonian for experiments? Right? For molecules, they're really a different beast than atoms. You see, molecules have a polarizability associated with them. Okay, atoms have a tiny one that you can neglect. Molecules have a large molecular polarizability. And so the light field that you use to make the optical lattice has a polarization, right? So now that polarization is going to interface with the polarizability of the molecule. So for atoms, whether you polarize your optical lattice this way or circular, none of this really matters all that much for most applications. Here, depending on the polarization, I can get a completely different quantum phase, for example. Okay, so already something is quite different. So I want to ask the question, when experimentalists take these molecules and they turn on an optical lattice, what's the first thing they see? Not by putting in 39 different microwave fields to create some beautiful condensed matter Hamiltonian, but what's the first thing that they see? That's what I'm addressing here. Okay? Another thing we can ask about is, what are the new phases in dynamics for a lattice of large qubits? Right? And qubit means a qubit, but instead of 2 internal states, you have many internal states. Molecules have many internal degrees of freedom, right? They have this hyperfine degree of freedom. They have some kind of rotational degree of freedom. This is supposed to be rotation, right? So what can we do with these internal degrees of freedom? There are models of quantum computing where you have very good fidelity inside of a qubit, but you have very lossy, or low fidelity interactions between qubits. That's an alternate model to an array of qubits. So molecules do offer something new. This work that I'm doing is complementary to some wonderful work on molecules done by colleagues of mine, for example, Peter Zoller at Innsbruck with Guido Popillo, Hans-Peter Büchner, Alexei Gorshkov, so Anna Maria Ray, so all really bright people asking the kind of question, how do you create a known Hamiltonian from solid state that's unsolvable in the context of molecules? That's complementary to my work, right? Okay, but very different. I'm asking not how do you make a known Hamiltonian, but what do molecules give you? What do they naturally show without a lot of work? Okay. So I want to remind you of a Hubbard Hamiltonian. This is one of the 2 kind of paradigms for quantum phase transitions in maybe 3 paradigms for quantum phase transitions. The other 2 are the quantum rotor, right, and quantum Ising model. Okay. So in the Hubbard Hamiltonian, you say you allow particles to move around a lattice. These particles have mass. So instead of spin, like an Ising model, they're particles, and they can move around these lattice sites, right? Or, if there are two on the same site, they actually interact. And that's what a Hubbard Hamiltonian does. It allows for motion, that's T. T stands for tunneling or hopping, okay, between sites. These are destruction and creation operators, A and A danger. This happens to be fermionic. This bracket here means nearest neighbor. It says that things only hop one site at a time. They don't skip sites. Okay? The interaction here is between particles on the same site. You see this site index I, tells you they're on the same site, just like I showed here. So if they're on different sites, they don't talk to each other. That's because the interactions are short range. You can imagine for molecules, the story will be very different. There's an internal index, sigma. For electrons, that takes on just two values, spin up, spin down. For molecules, that can take on hundreds of values. I'll use the same symbol sigma through my talk so you know I'm talking about an internal degree of freedom. Okay? In condensed matter, the Hubbard Hamiltonian is just a model. It's a model saying we have kinetic energy or energy of motion, and we have interaction. What can happen, right? In cold atoms, you can derive the Hubbard Hamiltonian by a series of well-controlled approximations from the complete description of a dilute quantum gas. So it is a first principles model. Okay. Let's talk about these different energy scales that give rise to different internal degrees of freedom in molecules. So I'm sorry this is so small, and I'm afraid this may not show up on your movie. So let me just point and read these things out loud. So single molecule energy scales, there's a large separation of scales. First of all, you have electronic structure. Okay, does everyone know that I'm plotting like energy as a function of the internuclear distance between the two parts of the molecule here? Okay, that's what these curves are. So first I have electronic structure. It's on the order of an electron volt or 10 to the 4 Kelvin. Okay, then I have vibrational structure, this, right? And this is on the order of milli electron volt. MeV does not mean mega, it means milli here, okay? And that's about 10 Kelvin. Then there's rotational structure, which I showed you here with this arrow, right? And that is micro electron volts, very far from the LHC now, and 10 millikelvin. And then finally, there's this hyperfine structure, which is pico electron volts, right? And is about 10 nanokelvin. Okay, and if you think about temperatures of ultracold systems, you know, they're between nanokelvin and microkelvin. So you can imagine that it'd be pretty easy to wash out the hyperfine structure if you're not careful. On the other hand, rotational structure, you're only going to be able to excite through a microwave in the system. Naturally, thermally, or any other way, you're not going to excite it because 10 millikelvin is very hot compared to micro to nanokelvin. So for that reason, we'll include one microwave field in our system in order to access this structure. Okay, that'll be the only extra thing that I put in. So again, large separation of scales. Electronic degrees of freedom have to do with coupling to the optical lattice. There's an anisotropic polarizability. I referred to that 2 slides ago. Rotational degrees of freedom coupled to a DC electric field. That's what orients this molecule. Quantum mechanically, this molecule could be in any direction, right? So even if it has a dipole, you know, something like this, right? I don't know which way that dipole points. So the statement permanent dipole moment is very misleading for molecules. It's only permanent if you put an electric field on the problem. This is not like a ferromagnet or something. Okay. This is accessible via a microwave field, as I said, gigahertz field, and then the hyperfine structure couples to a magnetic field. Now for me, this wasn't announced, but I did my master's degree actually at CERN, and then I switched into condensed matter. And so I did my master's degree in heavy ion physics in the predecessor to RIC, an NA49. We were looking at quark-gluon plasma, and as part of my training, I studied a lot of nuclear physics. I was very pleasantly surprised to find nuclear physics reappearing inside of ultracold molecules as the key player. So this quadrupole moment, this is the nuclear quadrupole moment, actually. Now, and this comes from coupling of the distortion of the nucleus to the gradient of the electric field over the system. And this is actually what mixes the hyperfine structure into rotation. I think that's very beautiful, the way these fields come together. And what I'll show you is that there are many accessible internal states, and we can control them. So even though this looks like a mess, right, we can actually control each scale one by one because of the large separation of scales. Okay. So I'm going to show you a schematic I think I have this picture, and then I'm going to go on to show you lots of math. Okay? And then we'll come back to more schematics. So here's the experimental setup. I have some laser beams. They propagate equal and opposite to each other and make an interference pattern, a standing wave, right? In the wells of these laser beams, for example, the molecules can sit. These are the molecules, just like my molecule here. It's the same sort, so it's heteronuclear. One end is big, one is small. There is a polarization field as well as a intensity field for the lattice, right? Because polarization matters for molecules. So I have to take that into consideration. I have a 3D lattice. In actual simulations, I typically simulate 1D systems because I do entangled quantum dynamics. You can do 2D and 3D systems by Monte Carlo. It is difficult because of the number of internal degrees of freedom. Most of this Hamiltonian is still unsolved. Let's zoom in on just one well. So here's a molecule in one well. Can everybody see this green here? It's a bit hard in this projector. That's the DC electric field. So that's orienting the molecule. Okay? And then there is a magnetic field, and the magnetic field separately controls these nuclear spins. So you can imagine when these two fields are in the same direction, right, then we're going to have simultaneous good quantum numbers. And the system will be very simple. But if the fields are in separate directions, yeah, we won't have a simultaneous basis. Electric field and magnetic field will couple in some complicated way, and we'll get lots of internal states. That's the basic idea behind tunable complexity. I'll tell you more in a minute. Okay, without further ado, here comes the molecular Hubbard Hamiltonian. So keep in your mind, the Hubbard Hamiltonian originally had just energy of motion, right, and interaction. So this is going to be like that, but more complicated. Okay, the first term is the detuning. So again, this is a number operator. That's site I and internal state sigma. Internal state sigma can include many degrees of freedom. It's a catch-all for hyperfine, rotational, vibrational. Okay? By detuning, I mean that each of these internal states has a slightly different energy. Okay? The second term is hopping. Now, hopping looks just like the Hubbard Hamiltonian, right? I destroy a particle on site J, I create a particle on site I, but there's something that's different. This T, the strength of the hopping, the tunneling, depends on the internal state sigma. Okay? That's especially true for rotational states. So if my state is not rotating, right, it's going to present a different effective polarizability to the lattice than if it is rotating. Yeah? So if I change rotational states, I can instantly change from one quantum phase to another, for example. Okay, another thing is that I don't necessarily have only nearest neighbor hopping. And I'll explain why that is in a minute. So I say I and j are less than some maximal radius of hopping that I'm going to keep. Okay, the next set of terms looks complicated. This is an interaction term, and I divide it up into two pieces because these two pieces do very different things. It's a dipole-dipole interaction. The first piece is a number-number kind of interaction. So it doesn't change the internal state. It's just like that Hubbard model interaction. It depends on internal state sigma, sigma prime. Okay, and it operates at a radius less than RU. So another thing that people do in dipolar gas on a lattice is they take the dipole-dipole interaction to be infinite in range, and they take hopping to be only nearest neighbor. I think that's totally wrong. Okay, that's why I put this in here. I'll explain why I think that's wrong in a minute. So this is called the direct dipole-dipole term. It's a number-number interaction. This is called the exchange term. Okay? And I'll show you where these terms come from. The exchange term actually destroys two internal states and creates two others. There is a conservation law on these internal states, and all the exchange term can do is mix up states. It can't create new states. So if I change one internal state, another one has to come up. Overall, I have to conserve energy. Okay? So I'm going to call them U and E. And then the last term is that microwave field I mentioned. Right? I said if I want to access my rotational structure, it's gigahertz. There's no way to get to it thermally. I have to put one microwave field on the problem. That's my one microwave field. So it's going to be resonant between two internal states. And then I can think about off-resonant transitions as well. So I'm on the same site I, but I destroy a particle at internal state sigma prime and create one at sigma. So it changes the internal state. Okay, so four kinds of terms. let me say at this point just slightly more about what I mean. This is really for experts in the audience, but about what I mean about not having infinite range dipole-dipole interactions. The way that you derive a Hubbard Hamiltonian, I don't go through the derivation here, but the way you get it is you start from a continuum model, you turn on a lattice, you put things in terms of a Wannier basis, right? And then you drop out irrelevant terms. If we were to keep all possible terms, it's much more complicated than this. Yeah? A lot of these terms are negligible. That's why we drop them. We don't need 5,000 different terms. Yeah? But if you want to keep terms, you have to keep them consistently. You can't keep a bunch of terms all the way down to 0.001 hertz and then drop another set of terms that's below 1 hertz. You have to have a self-consistent truncation. So if you want to do that, this hopping term, may require, let's say, next nearest neighbor or next nearest neighbor. And certainly the dipole-dipole interaction will not be infinite range. At infinite range, the dipole-dipole interaction is infinitely slow. Okay? So you have to keep these terms self-consistently. So I would say look out a bit when you see theory models that don't do this. Okay. I want to show you a picture of how I think about this complex Hamiltonian. So here we go. I think about it as being effectively a kind of two-dimensional problem. So one set of dimensions, could be 1D, 2D, or 3D, is the spatial degrees of freedom. Another set of dimensions, or degrees of freedom, are the internal degrees of freedom. And why do I think about it as being basically 2D? I mean, the number of spatial degrees of freedom is typically about 100 lattice sites. Yeah? Do you guys know that? When you make these interfering laser beams, there's a kind of overall waist to the laser field. That means you can work with order of 100, 500, some small number of sites, certainly less than 1,000. And at some point, you need an overall trap to stop things from spilling off the edge. So this is not like solid state where you have Avogadro's number of sites. It's not even like nanodevices where you still have a lot more than 100 sites. You probably have 1,000, 10,000, 100,000. Okay? These are small systems. They're very finite. Well, the number of internal degrees of freedom, let's say for potassium rubidium, with one microwave field, keeping only the first two rotational states, is 144 states. So from the point of view of a theorist, this is basically a square lattice, even if spatially you have 1D. So let me now show you the molecular Hubbard Hamiltonian in words and show you how it moves you around this grid. So first of all, spatial hopping, right? That moves you up and down these spatial degrees of freedom. Particles move along the lattice. Spatial interaction happens, again, along the spatial degrees of freedom. And it's relatively long range. You're going to keep probably many sites out. Maybe not 100, but let's say at least 10 sites out. On the other hand, detuning controls the whole structure of this other set of degrees of freedom. Right? This sort of reorders the relative energies of each of these grid points. So like this might be high energy, high, low. Okay? And depending on what you do with detuning, you can change that relative order. So that's something like disorder. It also controls the lattice size, how many degrees of freedom are accessible. Internal hopping, driven by my microwave field, moves me up and down this axis. Okay? Internal interactions allow interaction along this axis. And then finally, exchange terms allow for internal two-particle hopping, so rearrangements of particles up and down this internal degrees of freedom. Yeah. So that's how I think about molecular Hubbard Hamiltonian. If you dissect it that way in your mind, in my view, it becomes less complicated. Right? This is the old Hubbard piece that we all know and love, this purple part. The blue part is all the new stuff, but it's really dealing mainly with a different set of degrees of freedom. Okay. So you can think about molecular Hubbard as being Hubbard Hamiltonian, the purple stuff, plus this new direction. Okay. So let me give you some more details of where this Hamiltonian comes from by going into the molecular physics just a little bit. I know this looks really complex, but I simply can't resist showing how cool molecules are. When I got into molecular Hubbard Hamiltonian, I was a many-body theorist. I didn't know the first thing about molecules other than, I breathe O2, I think. So, along with some other carbon, I think. So like I really knew almost nothing. And getting into molecules, I've realized how beautiful they are and just how complex they are. These are just diatomic molecules, imagine. Okay. So my Hamiltonian has 4 pieces, right? So I have internal degrees of freedom. I have external fields that control my system. I have my optical lattice, and then I have a dipole-dipole interaction. So let me show you these one at a time. So first of all, the single molecule physics, like I said, very pretty. Just the internal degrees of freedom. There are rotational terms, scalar, tensor, quadrupole terms. There are lots of things going on. So, for example, I1.I2, that is a coupling between the spin of one nucleus and the spin of the other nucleus. Okay? There's also a tensor part of this coupling. There's scalar and tensor part. This is the nuclear quadrupole. This tilde is referring to a quadrupole operator. And V sub I is the gradient of the electric field. Okay? So N is for rotation. I is, again, for the spin inside. Okay, the strong fields, how do they couple in? They couple in interesting ways. For example, of course, the magnetic field couples to the spin of each of the nuclei. You have coupling between the magnetic field and rotation. Here is my DC electric field that's orienting my molecules, and here is my driving AC field, my microwave field. I'll come back to this term later. It's really important. Okay, parts leading to the many-body physics. In the optical lattice, we have hopping terms, and you can see that, absolute value of E squared is the intensity. There's the lattice, but sandwiched in the middle is the polarizability, alpha, right? So that polarizability tensor interfaces with this optical field and with the polarization of this optical field. This is just the kinetic energy, which usually goes into hopping. And then finally, dipole-dipole interactions look just like you expect it to, straight out of a textbook. Nothing that interesting there. Okay, so how do we control all this physics? So here we go with experimental controls. So I'll first give you a summary, and then I will give you 4 slides on different specific knobs you can use in experiments, individual knobs to control these things. All right, so this is the overview. So first of all, my DC electric field, okay, mixes rotational levels. What are these pictures? These are supposed to be spherical harmonics, right? This is like the 0, 1, 2 spherical harmonic. So N is used for rotational states. I put a little bar over it to let you know that the basis I work in, for experts in the audience, the basis I work in is the one that is adiabatically connected to the zero field basis. Okay? That's what's going on here. So I can control these dipole moments with DC electric field, and I can mix rotational levels. Let's focus in on just N equals 0. Okay. So I'm sorry, this is somewhat washed out on this projector. Hopefully you can see this. This is the energy as a function of magnetic field. This is low magnetic field. That's high magnetic field. And I'm showing this for 3 different molecules. One of them is potassium rubidium. That's the one at JILA. One is lithium cesium. That's the one at Heidelberg, and exactly why I'm there right now. And one of them is rubidium cesium, and that's the one at Innsbruck. Okay? All 3 of these molecules are being worked on right now in experiments. And what you can see, hopefully, is that as I change the magnetic field, there's a lot of mixing of these hyperfine states. Okay? So I split the hyperfine states with the magnetic field, and I can tune the transition dipole moments via an angle between electric and magnetic field. Finally, the AC microwave field accesses internal states. That's that internal tunneling I was talking about. For example, I might drive N equals 0 to N equals 1 transitions. Okay. Finally, the optical field provides the lattice potential, and the polarization couples to anisotropic polarizability. So you want to ask me a question about molecules? It's going to get more complicated. Molecules are complicated things.
Back a little bit. In the previous slide, you showed that the dipole-dipole interaction falls as one of our cube. But in the previous slide, you said that you were going to throw away the long range and keep just a certain range, RE and RU. The next slide is what you want to do. Show our results with R cube or the short range.
Okay, so the question is, I said that I would throw away terms that were too long range, and yet I have a 1 over R cubed. Why am I throwing out those terms? Is that right? And which terms will I throw out? Okay, the answer is that I will throw out terms that are too slow for an experiment to ever see. So experiments, for example, last a second, maybe 10 seconds. Let's say a second. That means any terms that have a scale below 1 hertz are irrelevant for experiments. You'll never see any dynamical effects. The term will never matter, right? So if I imagine a dipole-dipole interaction that's 1 site out, that might be 1,000 hertz, 2 sites out, 100 hertz, 3 sites out, 1 hertz. Say, by the time I get to 4 sites out, it's sub 1 hertz, I throw it out. Okay. So there's a difference between applying a molecular Hubbard Hamiltonian to real experiments and an imaginary Hamiltonian where we would keep all possible terms because we imagine infinite times. I'm interested in the experimental application because the question that I posed at the beginning to drive my research is, what is the first thing experimentalists will see when they put molecules in optical lattices? Does this address your question? Okay. How many terms I keep will depend on the particular molecule, and that's a very interesting point that I'll come to later. So let's go on. Good. So 4 slides on experimental knobs. This is the first one. How do I control the hopping? Okay, I have 3 knobs for hopping. The intensity of the lattice, that's the same as for atoms. The DC electric field, actually, that's quite different than atoms. And the polarization of the lattice, right? So 3 knobs instead of just 1. For example, if I talk about how the internal state is affected by intensity, can you read this? This is the hopping of rubidium cesium. This is the 0,0 state. This is the 1,1. So this is the lowest rotational and first rotational. Sorry, am I pointing to the right thing? Yeah, for rubidium cesium, 0 and 1. Okay, so you can see that this is a log scale. The tunneling energy is different by, say, an order of magnitude for some reasonable intensity of your laser fields, kilowatts per centimeter squared. Okay, so just by changing between rotational states, I get a completely different hopping by an order of magnitude. And this transition is accomplished through a microwave field on the problem. Okay, let me show you what the electric field does. So this happens to be potassium rubidium, again the molecule at JILA. If I have an electric field, this electric field is now measured in kilovolts per centimeter, and I can ask, what is the polarizability, and here are the 4 lowest states I would access. I'm sorry these colors are a little hard to see, but here is the electric field, and here is the polarization of the lattice orthogonal to it right now. Okay, and you can see how these states change strongly with electric field, right? How the polarizability changes strongly.
You don't care about the external field, right? But any AC start shift caused by the lattice itself, you throw away those concepts.
Okay, the question is, do I consider the AC stark shift caused by the lattice itself or only external fields? And the answer is I consider both. Yeah, the AC stark shift is what gives rise in the first place to how we trap the atoms, right?
No, but considering the polarizability and everything.
Yes.
It's included there.
Yes. Yes. In our first paper in New Journal of Physics as part of a special issue in which my review also occurs, we include every possible term under the sun. In our second paper in PRA, we drop many of the more negligible terms and we have a simplified version. I am now showing you a slightly more simplified Hamiltonian. The very general one, the first one we did, includes everything. Yes. Okay. You can see that if the electric field and the lattice have the same polarization, that these states take a totally different direction. One goes up, one goes down, right? So completely different effect. This was for potassium rubidium. I can also ask about rubidium cesium, and you see that for a different molecule, I have a totally different dependence of polarizability on electric field. Okay, so by changing molecules, I see very different kinds of hopping. It's not just the mass of the molecule. Okay. Second experimental knob, dipole moments. So I'm plotting here the log of the dipole moment. This is the dipole matrix element between internal state sigma and internal state sigma prime. Okay, and I'm going to show on each axis the 0 and 1 plus or minus 1 states. Let me say what I mean by that. So we have n and m sub n, the projection onto the z-axis of the rotational degree of freedom. So these could be 0, 0, 1 plus or minus 1, and 1, 0. So even with one microwave transition, right, I'm still going to have 4 rotational states. Each of those 4 rotational states then has many internal states from hyperfine degrees of freedom as well. So like for potassium rubidium, that's 144. Because there are 36 internal states, 4 times 9. Yeah, 4 from one nucleus, 9 from the other. That gives you 4 times 9. Times 4 from these guys gives you 144. Okay. So for example, one way that I could change dipole moments is through the B field angle. So here the angle of the B field relative to the electric field is 0. And you can see that most of the dipole moments are 0. Okay. Now I make the angle 90 degrees. Up, many of them are very big. These blue regions are forbidden, by the way. Okay. I could also change the B field strength. So I go, let's say, from 80 Gauss to 180 Gauss. And I will see a very different pattern in the dipole moments. I can also change the E field strength. So this is the strength of the electric field scaled to the rotational constant. That's the right scaling for this problem. And here is the dipole moments. And you can see that, depending on the electric field, I can get very different values, up to an order of magnitude change in various dipole moments. And then finally, I can change the species. So this is potassium rubidium, that's rubidium cesium, and that's lithium cesium. And you can see that I get, quite different kinds of dipole moments. Okay. The third experimental knob is the dipole-dipole interactions. And I just wanted to give you a tiny bit of a sense of how I do these derivations. This is just a little sketch. But the way I do it, here's this dipole-dipole term, which you probably all know from textbooks, I hope. Okay? And, this potential is a product of spatial and internal parts. So for the spatial part, we use spherical harmonics and the power law. And then the internal part is the dipole operators. Okay? I reformulate my dipole-dipole term in this manner. In terms of the energetics, I need my rotational projection to be conserved because I have this electric field, right? And then I use Wannier function overlaps to get the Hubbard parameters. So this goes in just, in a couple of steps, and what comes out is something like this. Okay. So without filling in the details, because that would already be 30 minutes of discussion, what we end up with are these two processes. These are the direct and exchange processes that I discussed. The direct process leaves the internal state unchanged. That's just like the Hubbard interaction. Okay? The exchange process actually swaps a rotational quantum. So you see what happens is, this is again my spatial degrees of freedom. These are my internal degrees of freedom. And you can see that, for example, one molecule might go down and the other go up. That's what the exchange does. Sort of a flip-flop term, if you wish. Questions on direct versus exchange? Okay. Same sort of thing happens in magnetism, by the way. Experimental knobs 4. I'm just going to summarize this. This is now unpublished. But it's fine to be on TV. So it turns out that, there's another misunderstanding in the literature about dipolar gas that we were very surprised to discover by accident, just by checking corrections and things. And so one misunderstanding I said is that it's not really infinite range. In practice, it's not. Okay? And the second is that it's not really 1 over r cubed. That was a surprise to us. So if you try to make reduced dimensionality, like you try to make 2D planes of a dipolar gas by confining your BEC, you find out that this confining field significantly modifies the dipole-dipole interaction. So for example, even for a moderate 2D scenario, you're just compressing a little bit, 100 hertz transversely, something like that, you'll find the magnitude is off by about 40% if you just do 2D versus 3D calculations. And the functional form is also modified. So this r to the minus 3 becomes more like r to the minus 3.1 to 3.5. Okay. So it's really only the isotropic 3D lattice that's purely dipolar. Yeah.
So how do you get these results? Are you going to explain them?
Well, I haven't published it yet. So I'll just tell you that I've calculated this, and I promise I'll back it up soon. I don't want to say too much because I think this is actually really important. So it's going into a PRL that I'm submitting, in a few weeks. Mm-hmm. Okay. With a lot of numerics is the basic answer, but yeah. Okay, so now, I understand that there are a few experimentalists in the audience. Is that correct? And so as a theorist, I thought that I should put up some numbers. This is always dangerous for theorists to do, but fortunately, most of these numbers were calculated by theory, by density functional theory, okay, from chemists. Very few of these things have been measured experimentally, and that's actually a challenge to experimentalists to do this. So there's a lot of kind of, basic molecular physics that is not done for these molecules. So I want to give you a sense of how different molecules are. So this is, again, potassium rubidium at JILA, rubidium cesium at Innsbruck, and lithium cesium at Heidelberg, where I am, okay? And, there are lots of constants that go into the molecules. As I showed you when I showed you the molecular Hamiltonian, remember I said it was very beautiful? Okay, and I just want to point out one of them. So here is the nuclear quadrupole coupling. Remember how I said nuclear physics, my old field, came back into molecular physics and how happy I was? Look at how different these numbers are for different molecules. So for example, for potassium rubidium, I have 0.45 minus 1.41, okay? For lithium cesium, completely order of magnitude different, 0.0185, 0.188. Yeah? Another one we could look at would be the scalar spin-spin coupling. That's the coupling between the spins in the two nuclei. Look how different it is from molecule to molecule, right? So for potassium rubidium, minus 2,000. For rubidium cesium, plus 17,000, For lithium cesium, plus 1,600, okay? And units are all listed over here. I'm talking about hertz at the moment. So the point is that different molecules have very different physical constants inside. And that's what's going to lead to different many-body physics.
Excuse me, the two numbers that you have down there, are range? Do you range for them? Or
Okay, the question is, are the two numbers that I have down here the range? And the answer is no. I have two nuclei, and each has a separate quadrupole moment, right? So this is the first, for example, this would be potassium, and that would be rubidium. Yeah. And again, these are density functional theory calculations from very talented physical chemists, but I didn't do these calculations. They're not measured, so this is our best guess so far. No proof, no experimental proof. Okay, what about the lattice and many molecule scales? These can also be very different. And what I want to do now is focus on the outcome of these molecular constants on the many-body physics. So that's going to be basically the rest of the talk. And how am I doing on time? I don't have a clock. When did it actually start? Quarter of an hour. I don't think I'll need more than 10 minutes. So I just want to show you what the many-body outcome is for this physics. Okay. So I will talk about weak field and strong field regimes, and you're going to see this table of numbers like 3 or 4 times. And you see I have hopping terms here. T is hopping. Delta is my detuning. And then these U's are my direct dipole-dipole interaction. And E is the largest of the exchange dipole-dipole interaction. Okay, so let's see what happens to, with all of these numbers. These numbers come out of the molecular constants. So here we go. Different molecules have different natural regimes. What do I mean by that? Okay, for potassium rubidium, it has a very weak dipole. It's actually not really long range. So I was asked earlier about the range of the dipole-dipole interaction, and I stated that it would be very different for different molecules. Potassium rubidium is basically nearest neighbor. Anything past nearest neighbor really doesn't matter. Okay, and you can see that from the table. Okay, so in the weak field regime, for example, if we look at these interactions, this is in units of kilohertz. This is sub-hertz, right? It'll never matter, okay? So what happens in the weak field regime, the hopping is much greater than the exchange, is much greater than the direct interaction, okay? On the other hand, in the strong field regime, meaning I go from like a kilovolt per centimeter to more like 5 or 10 kilovolts per centimeter, I'll find that the hopping is still big. These are very mobile molecules, right? But exchange and direct terms are on the same order. And remember, exchange and direct terms do very different things, right? The exchange term actually trades around internal states. Direct term is more like a Hubbard interaction. Okay. So that's potassium rubidium. Not really long range. Basically, it's all about kinetic energy. Okay. What about rubidium cesium? Rubidium cesium is the most susceptible to electric fields. This has to do with the quadrupole moment, among other things. And it's best suited for the direct dominated regime. So in the weak field regime, here again are all the numbers. The exchange interaction is on the order of the direct interaction. Both are much greater than T. So I can even think of these molecules as being frozen out. They don't move at all. And I can talk about just internal degrees of freedom moving around the lattice, and that will be an effective spin model, actually. Okay? In the strong field regime, this direct term dominates over everything, which I think is kind of cool. So that's a great thing to do with rubidium cesium. By the way, rubidium cesium is already cooled directly into a lattice, so it's natural to look at lattice physics. Potassium rubidium is now actually in the lattice, just now in the last few months. Okay, lithium cesium is quite different than the other two. It has a very strong dipole moment, an order of magnitude bigger than potassium rubidium, like 5 dBi instead of 0.5 dBi. It's especially interesting for exchange physics for that reason. So in the weak field regime, the exchange term dominates over everything else. In the strong field regime, it's sort of similar to rubidium cesium. The direct and exchange terms are on the same order, and basically the molecules don't move around. Okay. So let me summarize what the many-body consequences are for these different molecules. Okay. Suppose I start with the AC field off, so no microwave on the problem, right? Then, no internal degrees of freedom are accessed, assuming I start off the molecules in the lowest hyperfine and rotational state. There are no transitions at all, and I have only spatial degrees of freedom, and then I get superfluid, supersolid, crystalline phases, all that beautiful story of the dipolar gas. It's already a very nice story. Now I turn on the AC field, so I allow this transition between rotational states. If I have a strong B field on, I can separate out only 2 states. So when I make this transition, I won't be coupled off resonantly to any other states. In that case, only two internal states are populated. If I have unit filling, I get an effective spin 1/2 model. It looks like a long-range XSC model, and that's the source of one of these mappings onto spin models done by, for example, Alexei Gorshkov and Anna Maria Ray and folks like that. However, in their work, they suggest that you should leave the magnetic field off. I disagree with this. If the magnetic field is very small, you get a lot of mixing of hyperfine states. So small magnetic fields make a problem, and you can't get rid of all of them in an experiment. So actually, the best thing is to have a strong magnetic field on. And then you get only the two states, and you get exactly what Gorshkov is predicting. If you have a strong field on, it's easy for an experiment because you already need this field for Feshbach resonance, right? So naturally, you have it. Finally, how about direct versus exchange terms? In general, if you have a small DC electric field, you have a large exchange effect. If you have a large DC electric field, you have a large direct effect. Exchange terms give rise to XY-like models in the internal space, and direct field gives rise to Ising-like models in internal space. So they really do very different many-body physics. Okay, if we work in the general field regime, where we have strong electric fields, reasonably strong magnetic fields, we have the AC field on, there's no comparison anywhere in solid state. So everything here looks at least something like something known from solid state particle condensed matter physics, but this is completely new. And this general field regime is the focus of one of my papers, and it's the focus of my future work in a lot of ways. I think all of this is very pretty. I like it, but I like that molecules offer something completely new. I call it a quantum complex system. So many internal states are populated. There is no simple spin mapping. We're dealing with emergent phenomena in complex objects, right? Nothing like electrons, much more complex than that. Okay, since I think I'm short on time, I'm going to skip these two applications and go to the conclusions. So in this talk, I've introduced the molecular Hubbard Hamiltonian. I've told you that there are 4 kinds of terms. The first one is the detuning. That controls the size of the internal lattice. The second term is the lattice. That controls the spatial hopping. Okay? The third term is the dipole-dipole interaction. That controls spatial and internal interaction and two-particle hopping. And finally, the fourth term is the AC electric field, and that creates internal hopping. So when I use this language, I'm referring to this picture I showed you where there are spatial degrees of freedom and internal degrees of freedom. And if you take something away with you from this talk, I would take away that what is molecular lattice physics? It's spatial degrees of freedom plus something new, the internal degrees of freedom. Okay, I've identified many new experimental knobs that were not known until this work. One very obvious one is the angle between the DC electric and magnetic fields. For example, in the JILA experiment, they just happened to have their electric field pointing this way, and their Feshbach coils arranged so the magnetic field was that way. Well, that causes lots of internal states to be populated. If they reorient, then they have, the simultaneous bases, and they don't populate internal states in the same way. So they're playing with that. And I showed you that different molecules show different emergent many-body features. Okay? So rubidium, cesium, rubidium, cesium, potassium, rubidium, and lithium, cesium, right, all have very different macroscopic effects. One should have several experiments in each molecule, right, because you always need more than one experimentalist working on something to have, complementary competing results, to make sure results are correct, to get different perspectives, right? So it's not enough to have one. Right now, we have one experiment on rubidium, cesium, one on potassium, rubidium, and one on lithium, cesium. We need a lot more experiments on molecules because they're really going to show different things. This work is published in a couple of papers, and there's a new paper coming out soon, and I thank you for your time.
Let's start the question section.
Yeah, I want to go back to the AC from the light that makes the lattice. Because if you have too many internal states, then each level, like the hyperfine, coupled differently to the AC structure. Therefore, it's like I have to see like a collection of lattices of different amplitudes depending on the state I am.
Okay, so the question is
that involved in the whole thing?
Yeah, I'll answer this specifically. The question is, what is the effect of having many hyperfine states coupling to the laser light field of the lattice. Okay? And the answer is that that's about a 1% effect. It's very similar to the hyperfine states of atoms, where, yes, there are small differences in lattice amplitudes, but they don't matter for the kind of many-body states we're looking at. The effect for rotational states is a factor of 2, a factor of 10 is huge. It's a 100% effect. The effect for hyperfine states is a 1% effect. So it does exist. We have it in our first paper, but not in our second one. We drop it out, and I'm not including that here because it's just so small. There are wavelengths. Is this a rainstorm? Wonderful. there are wavelengths okay. There are wavelengths you can go to where the hyperfine effects will be much bigger, but these are not accessible in experiments. They're just in pure theory. There are also wavelengths you can go to where it disappears, right? These magic wavelengths, where all these hyperfine states see the same lattice. But this also is very far off. So, yeah.
Yeah, moment. What can we expect when you consider more internal states? Do you get any new interesting phases, or do you have some idea what can be expected when you consider more and more internal states?
So the question is what do we get by including more internal states? Do we see new phases? Right. Yeah. So the answer is, for example, let me go to my third application. You see quantum dephasing. Okay? So what happens is, so this is the average. Can I turn the lights off so this can be seen better? Yeah. This is just one simple example. A lot more happens than this, but here's one we've actually simulated and calculated. It's in our paper published. So this is the average number in two internal states that I'm resonantly coupling through this microwave field. So the blue is one and the green is the other. And you can see that there are Rabi oscillations. They're very fast. Okay? Now if I change some parameters in the problem to have both a Rabi frequency such that the single and many molecule physics is actually coupled, yeah, then I'll find that some other internal states start to play a role. And what happens is these Rabi oscillations start to dephase because lots of many-body modes are being populated. That effect is increased greatly by having internal states. Yeah? And what you see is, over a long period of time, here is 800 milliseconds. Okay? This is actually for potassium rubidium. This is a real calculation with real numbers. In less than a second, you see total dephasing. There's an envelope for that dephasing, and the envelope depends on the kinds of internal states we access, how many we have, etc. So there is one dynamical example. In general, when you have a complex system that has multiple scales, like this problem, you get into emergent phenomena, and by emergent phenomena, I don't mean, like hardness or something, or like this table is somehow an emergent phenomena of the little bits. I mean something more like the Great Red Spot on Jupiter. So you get sort of global excitations that you wouldn't, that are persistent for long periods of time. They may not be stationary solutions, but they'll be long-lived, and you would not have predicted them from a few particles. Okay, and we anticipate that kind of thing. We have some preliminary ideas about that, but nothing I want to state in public. Yeah, and you need to do an averaging procedure to see that. And one thing you can imagine doing is, let me go back here. You remember this picture I had of the dipole moments? Is trying to do a kind of a functional fit over these dipole moments and having a continuum picture of the internal degrees of freedom. So if I have several hundred internal degrees of freedom, I can do a continuum approximation instead of just thinking about a simple lattice. That's the sort of direction that we're going in. In the same way that you'll think about long wavelength phenomena in a lattice, you can, in a spatial lattice, you can do the same internally. Yeah.
Perhaps it's a naive question.
Can you speak up because the rain is very loud?
It's a naive question.
Naive questions are great. Go on.
What about fermions? Is it possible to do this with fermions?
Okay, so the question is, what about fermions? Can you do this with fermions? I never specified statistics in this talk, and no one asked me until now. The answer is that actually I have been doing fermions. I've allowed occupation of only one molecule per site, maximum. The reason is that some of the molecules I'm looking at undergo chemical reactions if they're on the same site. Even if they don't undergo chemical reactions to reform dimers, they undergo rotational and hyperfine relaxation. Okay, so all these molecules have problems when you put them on the same site. By keeping my electric field oriented, so the molecules are repulsive, then they don't ever occupy the same site. No? And so then, doing fermions is very reasonable. I still need one band. I can do fermions and bosons. It only becomes more interesting in 2D. The simulations that I do, which is, sitting behind this picture, these are entangled quantum dynamical simulations using time-evolving block decimation and other more advanced matrix product state methods, and they really only work well in 1D. So in 2D and 3D, we can do some statics, but dynamics is rather difficult. Yeah. But yes, I would love to do a mean field theory of bosons in the lattice in like 3D. That would be very cool. Good.
Maybe a little comment. I could say that since you allow lots of internal degrees of freedom, you're going to the large n limits on solving your problem. In the large n limit, there are many techniques on that, and much is known about the result of behavior.
Okay. The comment, right? Yeah. The comment is, what about the large n limit? We know a lot of things about large n limit, for example, for large magnetic spin, and why haven't I used those techniques here? Okay, the answer is, first of all, this is more complex. At the very least, we have 3 interfacing spin manifolds, right? One is the spin of one nucleus, one is the spin of another nucleus, the other is the rotational degrees of freedom. So at best, it's a large 3n limit in some sense, okay? There are 3 different n's. MNL, perhaps. That's first thing. Second thing is, it's an interesting fact that even for fairly large spins in real physical systems, if you go to the large n limit, you get some things wrong, quite a lot of things wrong. So magnetism is funny that way, where going to the large n limit gives you deceptive results. So even if n is 10 or 20, or even 100, a lot of times the large n limit is wrong. If by large n limit you mean mean field theory and going to large numbers of dimensions, that I call large z limit. Okay, that we can certainly do, yeah. But I think large n limit is dangerous in this case because our number of internal states is really not so big to justify that. It's 10 to 100. It's not 1,000, 10,000. In parallel with magnetism, I've seen dangers of that before, and moreover, this is a complicated limit because it's 3 different n's. But it's a good question. It's something we've thought about. We would love to use it.
Inside of your large n, it's not all of them except 3n.
Right. The comment is that there is some anisotropy inside my large n because there are different n's. That's correct. Yes. Good. Thank you. That was a great comment. More questions?
So, Nico, you were showing the case for revealing potassium. While if you have 144 levels, which I think are the molecular levels, all the relevant molecular levels that you can see. So in this case, you would have to, for all the different effects that are you considering here, AC, there, start shifts, AC coupling, and so on. So when you calculate those things, you have to diagonalize the whole for the state. How do you actually practice that? Or there's some approximation that you break that in parts and so on. So you just...
Okay, so the question is, we have 144 internal states for potassium rubidium, even if we do only one rotational transition from n equals 0 to n equals 1. Doesn't that seem like a big matrix? How do I deal with that numerically? The answer is I simply do exact diagonalization. It's pretty straightforward, actually. So in terms of diagonalizing quantum many-body problems, the single molecule problem is straightforward.
And in which basis? What basis do you take in this case? You take I,
Okay, so this I mentioned, the question is what basis do I use? And this I mentioned just momentarily in passing when I said, oh, this is a point for experts earlier in the talk. I used the basis that's adiabatically connected to the 0 electric field states, okay? Yeah. Now the many-body problem, the many-molecule... Sorry?
So you start L, S, I, J, whatever, and then depending on the regime that you are, you adiabatically follow that.
So I adiabatically start with... Yeah, so I start with 0 electric field, I solve the whole problem, and now I adiabatically connect those states to wherever I want to be. I rediagonalize, and then I do my simulations there. So my simulations right now are not going to treat oscillating electric field. They're going to treat fixed electric field, fixed magnetic field. The only oscillating field in the problem is my microwave transition, right? If I wanted to suddenly change my DC electric field, I would have to come up with a different simulation technique a different set of bases. Okay, my technique right now is matching present experiments. Future ones might do something really very different, and then I'll have to change it. That's a very interesting problem we can discuss later because it comes into what I was discussing with you over lunch about Fermi resonance Hamiltonian and how fermions pair in the lattice, and a really much more basic question than this one about how to set up bases appropriately in the lattice. So I do want to mention how I solved the many-body problem. So I solved the many-body problem right now in 1D using matrix product state methods. Okay? And typically, the actual number of internal degrees of freedom I have is 30 or 40. The reason is that matrix product state methods don't scale very well with the on-site or single molecule dimension. So that's usually called like local Hilbert space dimension. And these methods scale as d cubed. So that's called d, right? So they scale as like d cubed. So obviously, 40 cubed is pretty bad, right? So it's not the single molecule physics, but it's the algorithm for the many-body physics that limits me to some smaller number of internal states. It's exactly why this excellent question asked earlier is so important about how I'm going to treat these many internal degrees of freedom. I have to do some averaging procedure. After all, if we want to treat water, at some point we better stop treating water molecules and start treating, fluid dynamics, right? So I need something analogous here. Yeah. Good. Yes.
I don't understand how a dipole-dipole interaction, when you lower the dimension, it's not dipole-dipole any longer. Just tell me the main principle. Doesn't need a big explanation, just like a few words. How comes that is no more 1 over d cubed?
I'm gonna punt on that question since this is on TV, and then I will I will send you a paper later, in a few weeks, and answer it then. Yeah, I mentioned that as a teaser. Okay. Yeah, but I'll give it.
May be different.
Well,
but dipole-dipole is still dipole-dipole.
Well, I will give you simply a very qualitative statement, which is almost meaningless, but I'll at least make the statement for TV. Okay, so 2 molecules, right? They have dipoles. In 3D, they can sit in any place, right? And the 1 over r cubed assumes that you can occupy all these locations, right? But if they can't get up, right, the power law changes. So because you're changing the symmetry of space, the symmetry of the problem, yeah, when you squeeze, you cut off part of the interaction.
2D fields of dipoles, still they use 1 over d. But anyway, it's fine. I'm sure that.
Yeah.
I have to read the paper.
Okay, and the other thing to remember is, when you squeeze very tightly transversely, a lot of things change in scattering, right? So if you think about this old result from Maxime Olshany, perhaps it'll convince you that this might be the case somehow for dipoles. Okay, so even contact interaction.
To the effective interaction.
Yeah.
It's not like dipole-dipole will be always dipole-dipole.
Well, I don't know what effective interaction means here.
Well, when you adding other things besides the...
Yeah, exactly. The other thing is of course, dipole-dipole interaction is still 1 over r cubed. But I think I used the word effective. The effective power law is a little bit different from 1 over r cubed because of transverse squeezing. It's an effect of the confinement, right? Similar to this Olshany result where, just say this for the general audience, I know you know it, where you squeeze contact interactions and you end up even going through a resonance. They blow up. So, very different things happen when you add it, when you break the symmetry of the problem. Yeah, and the thing is, dipole-dipole is much longer range than contact. Okay, I mean, contact still has some range, right? It's a few hundred Bohr or whatever. And so it means that even pretty weak transverse squeezing has a big effect, unlike the case of contact interactions where you have to go down to, sub-nanometer scales or whatever.
Phase 2 when you start to squeezing it.
Yeah, so the comment is you limit the phase space 2 when you start to squeeze it. That's absolutely correct, and that comes into our calculation. Yes?